The inverse secant function, \sec minus $1. Hello everyone. In this subsection, we are going to explore the inverse of the secant function. Now, before we dive into the inverse itself, it is crucial that we first analyze the behavior of the original secant function. You see, we cannot simply invert the function across its entire domain and expect a consistent result. Over the next few slides, we will examine why this is the case and how we must restrict the domain to properly define the inverse secant function. Analysis of the secant function, \sec x. As we mentioned in the previous slide, before we can define the inverse secant function, we must first have a clear understanding of the original secant function. Let us begin by recalling its fundamental properties. First, it is important to remember that the secant function is the reciprocal of the cosine function. In mathematical terms, the secant of x is equal to 1 divided by the cosine of x. Now, let us analyze the domain, which represents all the possible input values for x. The secant function is defined for all real numbers, except for those values where the cosine of x equals 0, as division by 0 is undefined. This occurs at odd multiples of pi over 2. Therefore, the domain consists of all real numbers excluding the set of odd multiples of pi over 2, where n is any integer. Next, we need to consider the range, which is the set of all possible output values. Since we know that the value of the cosine of x always fluctuates between -1 and +1, its reciprocal, the secant of x, will behave differently. Specifically, the output will always be either greater than or equal to 1, or less than or equal to -1. To express this formally, the range is the union of two intervals, from -infinity to -1, and from +1 to +infinity. More simply, the range is all real numbers except for the open interval between -1 and 1. Understanding these specific properties of the domain and range is essential, because as we will see in the next slide, the periodic nature of the secant function prevents us from inverting it without first applying some restrictions. The necessity of domain restriction. Now that we have analyzed the general properties of the secant function, we must address a critical problem before we can define its inverse. In mathematics, for any function to have an inverse, it must be bijective, which means it must be both one-to-one and onto. However, as we know, the secant function is periodic. This means it repeats its values in a regular cycle every 2 pi radians. To illustrate why this is a problem, consider this example. The secant of 0 equals 1, and the secant of 2 pi also equals 1. Because we have two different inputs producing the exact same output, the function is not one-to-one, and therefore, it cannot be inverted in its current state. To resolve this and make the function bijective, we must restrict the domain. By limiting the function to a specific interval, we ensure that the function takes every value in its range exactly once. For the secant function, the standard restriction used globally is the interval from 0 to pi, excluding pi over 2. Within this restricted interval, the function is strictly increasing or decreasing in its segments. This ensures that the function is one-to-one, providing us with the necessary foundation to formally define the inverse secant function, which we will do in the next slide. Defining the inverse secant function, \sec minus $1. Now that we have restricted the domain to make the secant function bijective, we can formally define its inverse. This is known as the inverse secant function, which is denoted as secant inverse of x or arcsecant of x in simple terms. This function essentially reverses the operation of the original secant function. Let us look at the formal definition. If we state that y equals secant inverse of x, then it follows that the secant of y equals x. However, this is only valid provided that y falls within the interval from 0 to pi, excluding pi over 2, and x is any real number except those between -1 and 1. To understand the domain and range of this inverse function, remember the general rule. The domain and range of an inverse function are simply the swapped range and domain of the original restricted function we analyzed in the previous slides. Therefore, the domain of secant inverse of x is all real numbers excluding the interval between -1 and 1. This means that the input x must be either less than or equal to -1 or greater than or equal to 1. The range, on the other hand, is the interval from 0 to pi, excluding pi over 2. This specific range is referred to as the principal value branch. Consequently, any value of secant inverse of x that falls within this specific interval is known as the principal value. Illustrative example. Now that we have established the definition, domain, and range of the inverse secant function, let us apply these concepts to a practical example. Our objective here is to find the principal value of the inverse secant of 2. To begin, let us assign a variable to the angle we are trying to find. We will let y equal the inverse secant of 2. Next, we can rewrite this expression in terms of the original secant function to make it easier to solve. By the definition of inverse functions, if y equals the inverse secant of 2, then the secant of y must equal 2. As we recalled in our earlier analysis of the secant function, secant is the reciprocal of cosine. Therefore, we can substitute the secant of y with 1 divided by the cosine of y. This gives us the equation 1 over the cosine of y equals 2. By rearranging this, we find that the cosine of y equals 1/2. Now, we need to identify the angle y whose cosine is 1/2. However, we must be careful to look only within the principal value branch that we defined in the previous slide, which is the interval from 0 to pi, excluding pi over 2. From our knowledge of standard trigonometric values, we know that the cosine of pi over 3 is equal to 1/2. Before we conclude, we must verify that our result falls within the required range. Since pi over 3 is between 0 and pi, and it is not equal to pi over 2, it satisfies the conditions of the principal value branch. Thus, we can confidently state that the principal value of the inverse secant of 2 is pi over 3. Keep this process in mind, as we will see in the next few slides how avoiding these specific steps can lead to common mistakes. Real-world application context. Now that we have walked through the theoretical definition and a practical calculation, you might be wondering where the inverse secant function is actually applied in the real world. While the inverse secant function is perhaps less common in everyday conversation compared to the inverse sine function, it remains a vital tool in professional fields such as physics and engineering. Specifically, it is used extensively in optics, the study of light, and in structural analysis, where engineers calculate the stability of various builds. To give you a concrete example, imagine you are trying to determine the angle of a line relative to a vertical axis. If you already know the ratio of the hypotenuse to the adjacent side, which is the definition of the secant ratio, you would use the inverse secant function to work backward and find the specific angle. Understanding these applications helps us appreciate why the precise domain and range restrictions we discussed in the previous slides are so important for accuracy in these technical fields. Now, before we conclude, let us move on to the next slide to discuss some common mistakes students often make when working with this function. Common mistakes. Now that we have walked through the definition and a practical example, let us address some common pitfalls that students often encounter when working with this function. First, let's discuss a very common point of confusion regarding notation. It is easy to mistake the inverse secant of x for secant x to the power of -1. Please be careful here. The inverse secant of x refers specifically to the inverse function, which provides us with an angle. In contrast, secant x to the power of -1 refers to the reciprocal of the function, which is 1 over secant x. And as we know from our earlier analysis, this is simply equal to cosine x. Secondly, it is crucial not to ignore the domain restrictions we discussed in the previous slides. For instance, some students may attempt to calculate the inverse secant of 0.5. However, if you recall, the domain consists of all real numbers except those between -1 and 1. Because 0.5 falls within that excluded range, the inverse secant of 0.5 is undefined and has no real solution. Finally, be mindful of the quadrant when dealing with negative inputs. For example, if you are calculating the inverse secant of -2, you must ensure that your resulting angle falls within the second quadrant, specifically in the interval from pi/2 to pi. This is necessary to remain consistent with the principal value branch that we established earlier in the lesson. Key takeaways. To wrap up our session on the inverse secant function, let's go over the key takeaways to ensure you have a solid grasp of the concept. First, let's recap the domain. The input, x, for the inverse secant function must be either less than or equal to -1 or greater than or equal to 1. In other words, x belongs to the union of the interval from -infinity to -1 and the interval from 1 to +infinity. Next, remember the range, which we refer to as the principal value branch. This is the interval from 0 to pi, excluding pi/2. This restriction is what we discussed earlier to ensure the function remains bijective. As a practical tip for your calculations, as we demonstrated in our illustrative example, it is often much easier to solve the inverse secant of x by converting it into the inverse cosine of 1/x, since most of us are more comfortable with the cosine function. This conversion is a highly effective strategy. Finally, always keep in mind that the function is not defined for any value of x that lies strictly between -1 and 1. As we highlighted in the common mistakes slide, attempting to find the inverse secant of a value like 0.5 will not work because it falls outside the allowed domain. Keep these points in mind, and you will be able to handle inverse secant problems with confidence.